Hello students, now we will start numerical on type 1 system to draw the Bode plot for type 1 system. Okay, see I have taken the same numerical, only I have added one pole at origin. Okay, so look at this, sketch the Bode plot for the transfer function g of s as 1000 upon s in bracket 1 plus 0.1 s 1 plus 0.001 s. Okay, so first step we need to start. See, in this numerical also you have to calculate phase margin, gain margin and stability. Okay, so first step you need to do as s is equal to j omega. So look at this, here I have substituted s is equal to j omega. Okay, now next step I need to calculate the type of the system. So look at this, here there is a pole at origin, one pole at origin, so type of the system it will be 1. Okay, so we know that when type of the system it will be 1, starting slope, that is initial slope, it will be minus 20 dB per decade. Okay, so I have just concluded with type 1, initial slope minus 20. In previous numerical, type of the system is 0, so initial slope is 0 dB per decade. Okay, now next next look at this, starting point is 20 log k to the base 10. Actually I know that this is 60 dB. Okay, but for type 1 system we will calculate in a different way. Okay, so I am just not writing this point here. Okay, because in procedure I have given you the different procedure. Okay, so look at this, next step I need to calculate the corner frequency. Okay, now you are familiar with the corner frequency, this is a pole at origin, so it will not be having the corner frequency. So look at this, this is omega by 10, so first corner frequency it will be 10, then you need to rearrange omega by 1000, so this will be second corner frequency. Okay, now how you will calculate the starting point for type 1 system. Okay, in previous numerical you will directly get a starting point by calculating 20 log k to the base 10. So next step is actually step 2. On omega axis mark omega is equal to k is equal to 1000. Okay, again by the same thing I will draw the semi-log magnitude plot and the phase plot. In last numerical also I told you that you need to divide semi-log paper in 3 parts. First part you have to show it with the line slope of minus 20, minus 40, minus 60. Okay, then the next part is for the magnitude plot and this is for the phase plot. Okay, and this phase I will use for the calculation. Now see what I will do. I will start with the step number 1. First of all, show on omega axis, so this is my omega axis, show omega is equal to 1000. Okay, so this is omega is equal to k is equal to 1000. First step, from this point draw a line slope of minus 20 dB per decade. Okay, so how I will show minus 20 dB per decade. Okay, to meet y axis and this will be your starting point. Okay, so see this is my 1000, so from here look at this line, it will give me the line slope of minus 20 dB per decade. Okay, so see how I am just drawing. I am drawing the parallel line. Okay, so look at this. It will be always easy to draw the line slope of minus 20 dB with the help of roller scale. So please use roller scale. See, now I kept the scale in such a way that the line slope it will be minus 20 dB per decade. Okay, so this is a point at omega is equal to 1000 and see this line is intersecting the y-axis at 60 dB. Okay, so I will draw the line from this starting point at 60 dB up to first corner frequency. So what is my first corner frequency? My first corner frequency is 10. So I will draw the line only up to first corner frequency. Okay, so look at this how I have drawn, and this is actually the point. Okay, so this line will be having the line slope of minus 20 dB per decade. I hope you are getting. Okay, I have started from this point. Okay, I have not shown the dotted line here. Okay, this will always be your choice whether you want to show the dotted line. Okay, ultimately you have to draw the line up to first corner frequency. So first corner frequency is 10. Okay, now next from starting point I have shown minus 20 dB per decade. Next, then from the above end point to next corner frequency. So what is my next corner frequency? My next corner frequency is 1000. Okay, so from this point to next corner frequency, that is 1000, I will draw the line slope of minus 40. Why I will draw minus 40? Because previous is minus 20. Now my next factor is 1 upon 1 plus j.1 omega. So this is actually the pole. So this pole will contribute to line slope of minus 20. So what I will do, for getting the resultant line slope, I will add this slope with the previous one. So previous one is minus 20 and this is contributing to minus 20. So minus 20 minus 20, it will be minus 40. Okay, so look at this, how I will draw. So I need to take a line slope of, from here I need to take a line slope of minus 40 dB per decade. Okay, and I have to draw the line up to next corner frequency. So my next corner frequency is actually 1000. Okay, my next corner frequency is 1000. I will just take here. Okay, so from this next line, that is a minus 40 line, this is minus 40 line. Okay, so look at this, just like this, and up to next corner frequency is 1000. Why I need to check this? Because see, approximately I am drawing the line. Okay, so it is very important to check whether I am drawing the line properly or not. When you will draw magnitude and phase plot on semi-log paper, it will be easy for you to check whether the line is having the line slope of minus 40 dB per decade or not. Okay, so I have drawn the line with a line slope of minus 40 dB per decade. Look at this. I have started with this point where we have end. Then this is up to next corner frequency, that is 1000. Okay, now next step. After 1000, line slope will be, see, this is minus 40. Then this last factor is left, that is 1 upon 1 plus j 0.001 omega. So again this is a real pole and this pole will contribute to line slope of minus 20. Okay, so what we will do, now we will add this line slope with the previous line slope. So previous line slope is minus 40. So minus 40 and minus 20, it will be minus 60. Okay, so what I will do, again I will take a line slope from this as minus 60. Look at this. So I will extend like this, and up to infinity you can draw, but here just I am showing that this is a line slope of minus 60 dB per decade. Okay, so we have completed with a magnitude plot. Next I need to calculate the phase plot. Okay, look at this. You know that how to calculate the angle. Here pole at origin is there, so it will contribute to line slope of minus 90. So I have written here minus 90 degree, then minus tan inverse of 0.1 omega, minus tan inverse of 0.001 omega. Okay, so what I did here, I have directly written the values of omega and the calculation for phi. You need to do the calculation. So look at this, I know the scale for log omega, so accordingly I have taken the values 1, 10, 100, 200, 500. For that I got the values. Now I will put all these values in the phase plot. Okay, please select the y-axis for phase plot properly. This is for angle of j omega. Okay, so I will start at omega is equal to 1. Okay, this is my omega, this point, that is 0 for y-axis, and this is 1 for log omega axis. I am getting minus 95. So where is minus 95? So I may get minus 95 here. Okay, next for omega is equal to 10, I am getting minus 135. Okay, so minus 135, it may be here. So I am showing the point as omega is equal to 10. Look at this. So this will be my next point. Now next for 100, I am getting 1 minus 179.9. So approximately 180 degree. Okay. Then for 200, I am getting 188. Okay. So 200, it will be the second vertical line after 100. Okay. So for 200, I am getting minus 188. So where will be my minus 188? It may be here. Okay. So it may be here, minus 188. Then next for 500, I am getting minus 205.41. So for next 500, it will be in between 100 and 1000. So I am showing here as 200. It will be here. Okay, so now I will join all the points which I have plotted here. Okay, so look at this. I have completed the phase plot. Now the important thing, I need to calculate omega GC and omega PC. Now look at this. Here, this is a phase plot, and this phase plot is intersecting with minus 180 degree line at omega is equal to, look at this, it is intersecting here. Okay, it is intersecting here. So what I am writing, omega PC as 100. So this is 100 radian per second. Okay, what about this omega GC? Look at this. This magnitude plot is intersecting 0 dB line at again 100. So I am writing omega GC as 100. Okay, so please remember, when omega GC is equal to omega PC, what you will say? The system, it will be marginally stable, and in that case phase margin, gain margin, it will be 0. Okay, so see, I am just drawing the line now. See, for calculating, what I will do, look at this. Here actually I will extend from the point of intersection. Okay, so from omega PC I will draw the line that will intersect this phase plot. Okay, so it is intersecting same here. Okay, it is intersecting same here, no difference between 0 dB and a point of intersection. So what I will write? I will write omega GC as 100 radian per second. Okay, I will write omega PC as 100 radian per second. Okay, and I will write as omega GC is equal to omega PC. So gain margin is 0, phase margin is equal to 0. Okay, so what you will do, what you will comment on the stability. So I will write here, system is marginally stable. System is marginally stable. Okay, so when gain margin, phase margin is equal to 0. Okay, so when omega GC is equal to omega PC, we are getting system as marginally stable. Okay, so I hope you are getting. So this is the example for type 1 system. Thank you, students.